So now we're going to use that to solve some of these problems. This one says, find the length of OR. It's actually much simpler than you think. They do give us some details here. One of the key things that they tell us is the diagram below shows the rectangle BOAR. That rectangle part. When they say that, that's huge because rectangles have right angles. They have them in every corner. That's what a rectangle is. That means that this here is a right triangle. And so this distance OR that we are trying to find, I'm just going to call C, since it's like the hypotenuse of this triangle here. And that takes me to this formula, a squared plus b squared equals c squared. And so I want you to go ahead and try and use the Pythagorean theorem like we did in the previous problem to solve for C. Pause the video, give that a try, and then check back when you're ready to check your work. All right, so 5 should have been your A, and 12 should have been your B. Typically, I do the smallest one as the A, and the second one as the B, but this doesn't matter, right? Because 25 plus 144 is the same thing as 144 plus 25. So it actually doesn't matter which one you label as the A or the B. It just matters that you always do the hypotenuse as the C. That's all that really matters. When you add that up, you get 169, and the square root of 169 is 13, so therefore the hypotenuse must be 13. And that's nice. It's a nice, neat number. When you have integer numbers on all the sides, so 5, 12, and 13, not some decimal or some weird number, that's something special. That's called a Pythagorean triple. We're going to talk more about that next chapter. Something else to note here. I've told you in the past that when you take the square root of a number, you have to do both positive and negative, and that's true. However, in the context of geometry, we don't really have negative distances, and we're looking for a distance. So we'll never really use the negative when we're talking about geometry because we don't have a negative distance. There are some upper mathematics where this is still important, and this will come into play, so I don't want you to forget about this. But for now, we can just assume the positive value since we're talking about a distance. Okay? All right. Let's go on to the very last example, and this one is by far the most fun. So it says use the diagram above to find the missing segment lengths in triangle ABC. That should have said below. So let's take a look at this diagram. Now, there's something going on here. First of all, we have a big right triangle, and inside that is another right triangle and another right triangle. So we have two right triangles, two smaller right triangles inside of one big right triangle. When you have one right triangle made up of two smaller right triangles with shared vertices, see how they share this corner, all the triangles share this corner, and then the two triangles share this corner. Vertices and corners are the same things. The triangles are proportional. So this is huge. We know already that this triangle, this small one, is proportional to this one, and they're both proportional to this big one. So what I recommend in this situation is to redraw these three triangles. It's the easiest way to do this. The first step is a little bit tricky, but to redraw these all in the same orientation. By the way, I would strongly recommend that you write this down or just make a note of this, that these are all proportional. But let me show you what I mean by writing these all down in the same orientation. They all have a right angle, and they all have a small side or a small leg and then a longer leg. So I'm going to write them so they're all pointed, or redraw them so they're all pointed the same way. And I'll start with the really big one. And when I do the really big one, I'm going to do the short leg on top and the long leg on bottom. Okay, and if I was to do that, we know that the right angle in the really big one is C. We know the long leg goes down to point B, and the short leg goes to point A. I'm going to draw the other ones the same orientation. Notice I went from smallest or largest to smallest. Now looking at the middle one, this is the medium one, and maybe it'll help if I highlight this because it can get a little bit confusing. Okay, looking at that middle one now, what is the right angle? Well, the right angle is at point D. See how it's at D? So I'm going to label this point as D because D. Now I can see the short leg here is DC, so I'm also going to label this point as C. And I can see the long leg goes DB, so I'm going to label this as B. And I could do the same thing for the small triangle. I'll put that one here. All right. Well, if I do the same thing for the small one, the right angle in the small one is still D, so I'm just still going to call this D. But let's look at the short leg of the small one. Well, this DA, so I'm going to put the A here. And finally, we can see that the long leg of the short one goes to C, so I'm going to label this point as C. Now I'm going to fill in all the information. So I know that AD, wherever I see an AD, is really just 2. And I'll put these in blue so we can see a little bit different color. So that's 2. And that's the only place where there's an AD. But there's a couple places where there's an AC. We have AC here, and those are both 5. So I'm going to put those as 5. All right. And for now, that's all we know. However, we can get some more information really quickly because we have this little right triangle. We have 2 sides, and we just need the third. Well, we know a theorem that tells us that. It's Pythagorean theorem. It'll help us get that. So we could actually get this one here. In the big triangle, it's kind of like the height of the big triangle. So I'm just going to call it H. And I'm going to say that 2 squared plus H squared equals 5 squared. Remember, it's not just what you're looking for that goes all by itself. It's whatever's on the opposite side of the right angle. So 2 squared plus H squared equals 5 squared. And I'm just going to solve this out. It's not going to give us a nice, pretty number, but that's okay. So 2 squared is 4. H squared is just H squared. And 5 squared is 25. Subtract 4. Subtract 4. And so I get that H squared is equal to 21. Or H is simply the square root of 21. Whatever that is. So I'm going to put that over here, that this is the square root of 21. Well, and I'll put it here too. Well, remember, that's CD, and we have another CD here. So we can label that square root 21. All right. The problem asks for us to find all the missing segment lengths in the triangle ABC. That's this whole thing. So we still need to find BC, and we need to find BD, and then we need to find AB, right? And if we find BC, that'll be this side and this side. It'll be the same. Well, remember I said that these are all proportional. So we could label these whatever we want. Maybe we could, use some X's and Y's or whatever. So let's call BD X. Let's call this Y. Well, that means BD X we have here. And CB, which is Y, we have here, we have here. I'm just labeling them as letters because it'll make it a little bit easier to do the math. And then we have this whole segment AB, but we know that AB is simply going to be just whatever 2 is plus whatever X is. So we'll be able to find that one pretty easy once we find X and Y. Well, we have we have proportional triangles, so we could set up a proportion. So I know that the square root of 21 is to X as 2 is to the square root of 21. So I'm going to set this all up. I know I'm trying to find X, so I'm going to put X on top. So I'm going to say X is 2. And there's a lot of different ways. We've talked about all the different ways that you could set up proportions. But I'm going to say X is to this square root 21 because these sides correspond. So X is to square root 21 as this square root 21 is to 2. So, all right. Well, if that's true, we could just solve this. Again, pretty simple here. I have X being divided by square root 21, so I just want to multiply both sides by square root 21. So I'm just going to write that in here. Multiply both sides by the square root of 21. And that would cancel, of course. So I'd get X equals, well, this is kind of nice. The square root of 21 times square root of 21 is just 21. And so this is simply 21 over 2, or 10.5. And so now we found that this is 10.5. And now we could do a couple different things. We have 2 sides of this triangle. Therefore, we could use Pythagorean theorem to find y. Or we could set up as a proportion. I want to show you that both will work exactly the same. So I'm going to do it both ways here. So let's try and find y two different ways. First, let's use Pythagorean theorem. Well, according to Pythagorean theorem, again, this could be like my a, my b, and my c. So let's just write it all out here. I would say the square root of 21 squared plus the what is that, 10.5 squared has to equal y squared. Right? A squared plus b squared has to equal c squared. So let's just do this math here. The first one's easy. The square root of 21 squared, well, that's just 21. 10.5 squared, maybe worth just plugging in your calculator. 10.5 squared is 110.25. And this equals whatever y squared is. All right, 110.25 plus 21, that is 131.25 equals y squared. And then we're going to take the square root, And this is not going to be a pretty number at all, so we're just going to leave it in decimal form. But we get y equals, and you're going to have to do this in your calculator, square root of 131.25. And this is just an approximation. 11.4, and I'm going to round 46. So 11.46. Okay. This was all to find y. And here we did it with Pythagorean theorem, but we're going to find y as well. And this time we're going to use it as a proportion. I want to show you both ways so you know that both are options, and you could pick whichever one's easiest for you. So the other way is I see that y is the hypotenuse, and 5 here is the hypotenuse. So I could put y over 5, and I could set that equal to two known sides from both triangles. Well, I know that square root 21 is from the same triangle as y, and it should correspond to this side too. So since I put y on top, I'm going to put square root 21 on top, put that over 2. With some simple algebra, I could multiply both sides by 5, and I would get that y equals 5 times the square root of 21 divided by 2. Now, I don't really know what that is, but I could plug in my calculator, and you could as well. 5 times square root 21 divided by 2 is approximately 11.46. And so you see that you get the same thing either way. My point is to show you that there's a lot of different tools that you can use to solve these problems. And so you want to be able to have access to all of your different tools. All right, let's go up here. We know that x now is 10.5. We know that y is about 11.46. And therefore, we can actually figure out what AB is. And, AB is this whole thing. And it would just be 10.5 plus 2, right? It would just be this distance 10.5 plus this distance 2. So we know this whole distance here, AB, is equal to 12.5. And we could even write that here, 12.5. And so now we've found all the different side lengths. We started with just 2 and 5, and we found that this height down the center, that's square root 21. We found this is 10.5, and we found this is approximately 11.46. So with just 2 pieces of information and knowing that these were all right triangles, so these 2 pieces and knowing that these are all right triangles, we got 1, 2, and then 3 right triangles, we were able to find all the rest of them. And so that's pretty cool. It's pretty interesting. I know it seems like a lot of work, but it's definitely something that you guys are all capable of doing. All right, see you guys on the next video.